Combinatorics is a branch of mathematics that deals with counting, arrangements, and the combination of objects. Combinatorial problems often revolve around counting the number of ways to arrange or select a certain number of elements from a finite set subject to specified constraints. Combinatorics has applications in many fields, including computer science, cryptography, statistics, and optimization problems. Hello everyone, my name is Rafael. I am an electrical engineer, and in this video I would like to talk to you about combinatorics through 12 exercises with increasing difficulty as a preparation for exams. Let's go to the first exercise. Exercise number 1. A small community consists of 10 women, each of whom has 3 children. If one woman and one of her children are to be chosen as mother and child of the year, how many different choices are possible? Okay, my friends, this is the first question. Let's go to the solution by regarding the choice of the woman as the outcome of the first experiment. We're gonna have 10 possibilities. 10 possibilities for women, and the subsequent choice of one of her children as the outcome of the second experiment. We see that we're gonna have 3 possibilities for children because each woman has only 3 children. Then we have 10 possibilities for women, and each of them will allow for only 3 possibilities for children, okay? And then in this way we're gonna have 30 possibilities for mother and child of the year. Okay, my friends, very easy, isn't it? This is question 1. Let's go to question 2 now. A college planning committee consists of 3 freshmen, sophomores, 5 juniors, and 2 seniors. A subcommittee of 4 consisting of 1 person for each class is to be chosen. How many different subcommittees are possible? Okay, my friends, this is exercise 2. Let's go to the solution. The exercise said that a subcommittee of 4 is to be chosen, consisting of 1 person for each class. Okay, a subcommittee of 4. And 1 person for each of the classes, okay? We're gonna have 3 possibilities for freshmen, 4 possibilities for sophomores, 5 possibilities for juniors, and 2 possibilities for seniors. The result will be the multiplication of this. And we're gonna have then 120 possible subcommittees. Okay? This is the idea of the exercise. We may regard the choice of a subcommittee as the combined outcome of the 4 separate experiments of choosing a single representative for each of the classes. You're going to need to select only one person for each of the classes. We have 3 possibilities for freshmen, 4 possibilities for sophomores, 5 for juniors, and 2 for seniors. And then multiplying, we reach that we have 120 possible subcommittees. Okay, my friends, this is all for exercise 2. Let's go to exercise 3. Exercise number 3 now. How many different 7-place license plates are possible if the first 3 are to be occupied by letters and the final 4 by numbers? Okay, my friends, this is exercise 3. Let's go to the solution. The exercise says that we need to make license plates with 7 places. 1, 2, 3, 4, 5, 6, 7. The first 3 must be occupied by letters. And how many letters are available in the English alphabet? 26, isn't it? But let's suppose, before we use the letters, let's suppose that this is a valid plate. A, 1, 1, 1, 1. Okay? Supposing it is possible to repeat the letters and the numbers, so A, 1, 1, 1, 1 is a valid plate. There will be then, if we can repeat the exercise that did not impose this constraint, if we can repeat, and if the English alphabet has 26 letters, we're going to have 26 possibilities for the first position. As we can repeat, we're going to have also 26 possibilities for the second position and 26 possibilities for the third position. And how about the numbers? We have from 0 to 9, 10 possibilities. 10 possibilities for this position. As we can repeat, 10 possibilities for this position, 10 possibilities for this, and 10 possibilities for this. Okay? And if we multiply, we find a number equal to 175,760,000 possible plates. Okay? And this is the solution of exercise 3. Let's go to exercise 4, which is gonna be similar. In exercise 3, how many license plates would be possible if repetition among letters or numbers were prohibited? In this case, we're gonna have also 1, 2, 3, 4, 5, 6, 7. 7 places, but now repetition is prohibited. Okay? The English alphabet has 26 letters. Then for the first position, you're gonna have 26 possibilities. But as we already used the 1 here, we are not going to have available for us 26 possibilities. We're gonna have 25 now. Okay? Because we cannot repeat. As we cannot repeat, we are not going to use here the letter that has been used here. And for the third position, we're gonna have only 24 possibilities because the other 2 have already been used here. Okay? And this is for the letters. And how about the numbers? We're gonna have from 0 to 9, 10 possibilities for the numbers here. But as we already used one number here, we're gonna have only 9 possibilities for this, 8 possibilities for this, and 7 possibilities for this. And if we multiply them, if we multiply the possibilities, we find 78,624,000 possible plates. Okay, my friends? And this is all for exercises 3 and 4. Let's go to exercise 5 now. Exercise number 5. How many different batting orders are possible for a baseball team consisting of 9 players? Okay, my friends, this is exercise 5. Let's go to the solution. As each player has to take a turn and no repetition is allowed until all 9 players had their turn with the bat, we are dealing with a problem of a permutation, and the permutation is defined as the permutation of an element is n factorial, and as the team has 9 players, it is going to be the permutation of 9 players, which is 9 factorial, and this number is a very big number, 362,880 possible batting orders. Okay, my friends, this is the solution of exercise 5. Let's go to exercise 6 now. Exercise number 6. A class in probability theory consists of 6 men and 4 women. An examination is given and the students are ranked according to their performance. If no 2 students obtain the same score, letter A, how many different rankings are possible, and letter B, if the men are ranked just among themselves and the women are ranked just among themselves, how many different rankings are possible. Okay, my friends, this is the exercise. Let's go to the solution, and let's begin with the letter A. We have 6 plus 4, 10 students. We have 10 students, and as there can be no repetition, that is, no student can occupy more than one position in the ranking, it is a problem of permutation. Okay, but here we are ranking men and women together, not separately. In letter A, we are ranking them together. This is a problem of permutation, and the permutation of 10 students is equal to 10 factorial, and this is a very big number, 3,628,800 possible rankings. Okay, my friends? And in letter B now, men are ranked just among themselves and women are ranked just among themselves. This is also a problem of permutation, but differently, because men and women are being ranked separately. Since there are 6 men and 4 women and no repetition is allowed due to the aforementioned reason, we're gonna have the permutation of the 6 men times the permutation of 4 women, and this is equal to 6 factorial times 4 factorial, and this is equal to 17,280 possible rankings. Okay, see that when we combine the 10 students without separating them, the number of permutations is a lot larger than the number when they are permutated separately. Men are permutated separately and women are permutated separately. Okay, my friends, and this is all for exercise 6. Let's go to exercise 7. Exercise number 7. Sandy has 10 books that she's going to put on her bookshelf. Of these, 4 are mathematics books, 3 are chemistry books, 2 are history books, and 1 is a language book. Sandy wants to arrange them so that all the books dealing with the same subject are together on the shelf. The question: how many different arrangements are possible? Okay, my friends, this is the question. Let's go to the solution. Sandy has 10 books, 4 of which are mathematics books, 3 are chemistry books, 2 are history books, and 1 is a language book. Okay, and we are going to arrange them together like this. 4 positions for mathematics, 3 positions for chemistry, 2 positions for history, and 1 position for languages. The exercises said that it is paramount that all the books dealing with the same subject need to be together on the shelf. Okay? So, as there are 4 possibilities for mathematics, they can be arranged in these ways. Okay? We're going to have 4 possibilities for the first position, 3 possibilities for the second position, because there is no repetition. Okay? There is no repetition, and we already used 1 book here. So we don't have 4 anymore, we have 3. And as we already used the 2, 1 here and 1 here, we're not gonna have 3 anymore. We're gonna have 2 for this position and 1 for this position. And this is equal to the factorial of 4. Similarly, there are 3 chemistry books. We're going to have 3 possibilities for this position. As we already used 1 here, we're going to have 2 possibilities for this position. And as we already used 1 here and 1 here, for this position here, we have only 1 possibility. And this is the factorial of 3. Okay? The same for the history books. We have 2 possibilities for this position and 1 possibility for this position. And this is the factorial of 2. And this only 1 possibility for language books. And this is the factorial of 1. Okay? Alright? Additionally, we can permutate the subjects such as math, chemistry, history, and language, history, math, chemistry. Alright? we can also do the following. We have here maths, chemistry, history, and language. But we can also have history, chemistry, language, and math. This is one possibility, provided that this is the only constraint of this exercise, provided that the maths books are together, the chemistry books are together, and the history books are together. Then we can change their positions, and we can have language here, history here, maths here, and chemistry here, for example. And so on, so on. In this way, we will have 24 possibilities. This will be 24 possibilities. Okay? If we treat then 1, 2, 3, 4. This is going to be the factorial of 4. Okay? And this is 24 possibilities. We can change their positions and 24 possibilities. In this way, we're going to have 4 factorial times 4 factorial times 3 factorial times 2 factorial times 1 factorial, and this is equal to 6,912 possible orderings of her 10 books. Okay, my friends, this is all for exercise 7. Let's go to exercise 8. Exercise number 8. How many different letter arrangements can be formed from the letters pepper? Okay, my friends, this is the exercise. Let's go to the solution. If all the letters were different, the number of arrangements would be, how many letters do we have? 1, 2, 3, 4, 5, 6. If all letters were different, we would have the permutation of 6, which is equal to 6 factorial, which is equal to 720. However, it is not the case. As E is repeated twice and P is repeated 3 times, the real number of arrangements is, we're going to have the permutation of 6, but we need to discount or compensate for the repetitions of the letters E and P. And this is equal to 6 factorial divided by 2 factorial, 3 factorial. And this is equal to 60 possible arrangements of the letters pepper, okay? As there is repetition of the letter E and the letter P, we are not going to have 720 possible arrangements. We have to discount for the repetitions of the letter E and P, and in this way we have only 60 possible arrangements. And this is all for exercise 8. Let's go to exercise 9. Exercise number 9. A chess tournament has 10 competitors, of which 4 are Russian, 3 are from the United States, 2 are from Great Britain, and 1 is Brazilian. If the tournament result lists just the nationalities of the players in the order which they placed in the tournament, how many outcomes are possible? Okay, my friends, this is question 9. Let's go to the solution. As there are 10 competitors, the number of possible arrangements is, if we forget the nationalities and rank only the competitors, then it is going to be a problem of permutation, and the permutation of 10 is 10 factorial, which is equal to 3,628,800. However, as the problem stated that the tournament result lists only the nationalities, we have to discount for the repetition. Where there is repetition, we have 4 Russian, so there is a repetition here. We have 3 North American, there is a repetition here. We have 2 British, there is a repetition here. We have only 1 Brazilian, so there is no repetition for the Brazilian. Discounting for the repetition of the Russian, the North American, and the British, we find that it is a problem of permutation of 10 competitors, but discounting for the repetition of the Russian, the North American, and the British, we find that it is 10 factorial divided by the factorial of 4 times the factorial of 3 times the factorial of 2, and this is equal to 12,600 possible outcomes for this chess tournament, my friends. And this is all for exercise 9. Let's go to exercise 10 now. Exercise number 10. How many different signals, each consisting of 9 flags hung in a line, can be made from a set of 4 white flags, 3 red flags, and 2 blue flags if all flags of the same color are identical? Alright, my friends, that's the exercise. Let's go to the solution. We have 9 flags, of which 4 are white, 3 are red, and 2 are blue. Observe that as the flags of the same color are identical, we have 4 white, white 1, white 2, white 3, and white 4. We have red 1, red 2, red 3, and blue 1, blue 2, okay? This arrangement is precisely equal to, let's suppose, white 3, white 4, white 1, white 2, red 2, red 1, red 3, blue 2, blue 1, okay? So, observe that as the flags of the same color are identical, then this is equal to this, okay? Knowing this, we have to discount for the repetitions to obtain the accurate number of signals of 9 flags. We have a problem of permutation, the permutation of 9 flags, but we are going to discount for the repetition of 4 white flags, 3 red flags, and 2 blue flags. And then it is going to be the factorial of 9 divided by 4 factorial, 3 factorial, 2 factorial, and this is equal to 1,260 possible different signals with these 9 flags. Okay, my friends, this is all for exercise 10. Let's go to exercise 11 now. Exercise number 11. A committee of 3 is to be formed from a group of 20 people. How many different committees are possible? That's question 11. Let's go to the solution. Observe that it is a problem of combination, not permutation anymore. It is combination. If we select A, B, and C from the group of 20 people, we have 20 people available. Let's suppose that we select A, B, and C. If we select A, B, and C from the group of 20 people, all the permutations ABC, ACB, BAC, BCA, CAB, and CBA, 6. 1, 2, 3, 4, 5, 6. All the permutations of ABC will be counted if the order of the selection is relevant. If the order of selection is relevant, these 6 will be counted. They will be different. However, in this case, as we did with combinations, all of these 6 possibilities of combining A, B, and C will be counted as only one and considered as equal. We are going to consider them as equal and counted as only one, okay? Concluding, we will arrange 20 people in groups of 3. We have to arrange 20 people in groups of 3. Okay? For the first position, we have 20 possibilities. And we don't have any more 20. For the second position, we have only 19 because one has already occupied this position. And for the third position, we have only 18 possibilities. This is equal, this here is equal to the factorial of 20 divided by the factorial of 17. Okay? Observe that. And this is equal, the factorial of 20 divided by the factorial of 17 is equal to the factorial of 20 divided by 20 minus 3 factorial. And how do we interpret this? 20 is the total number of elements of the set, 20 people, and this 3 here is the number of positions, okay? We have this. This is our conclusion. N over n minus k factorial, where n is the number of possibilities and k is the number of positions to be filled. However, we need to discount for the repetitions. When we do this here, we are considering the repetitions. We have to discount for the repetitions. Okay? And here these repetitions here is the factorial of 3, which is equal to 6. Alright? Alright? And then we find the formula of combinations. The combination of n objects taken k at a time is equal to n factorial divided by k factorial n minus k factorial, and applying this to this exercise, it is going to be 20 factorial divided by 17 factorial, 3 factorial, and this is equal to 1,140 possible committees with these 20 people combined in groups of 3. Okay, my friends, this is all for exercise 11. Let's go to the last exercise, exercise 12. The last exercise, exercise 12. From a group of 5 women and 7 men, letter A, how many different committees consisting of 2 women and 3 men can be formed? Letter B, what if 2 of the men are refusing to work together? How many different committees can be formed in this case? Okay, my friends, so let's go to the solution. Let's begin with letter A. We have 5 women available, and the committee needs only 2 women. We are going to work with women first. Okay? The committee needs 2 women only, but we have 5 women available. Then we're gonna have 5 here for the first position, as there can be no repetition because 1 is already occupying this position. Then for this position we have only 4, and this is equal to 20. 5 times 4 is equal to 20. And what does it mean in this case here? It means that we are arranging 5 people, but we have only 2 positions for them. Then it is gonna be 5 minus 2, okay? And this is equal to 5 factorial divided by 3 factorial. Alright? We are using that expression that we understood in exercise 11. N divided by n minus k factorial. We are understanding the case of women first. However, in this calculation, we are counting AB and BA twice. Okay? We have many women here, 5 women, 5 for this position and 4 for this position. But in this case, we are counting, for example, we have A, B, C, D, and E. Okay? 1, 2, 3, 4, 5. We have 5 possibilities for this and 4 possibilities for this. But in this case, let's suppose we are taking AB. In this calculation here, we are counting AB and BC. And BA. And BA. Okay? Twice. Since the order is not important, AB and BA will be counted as one. They are equal. In this sense, we need to discount for the repetitions. Then we need to discount for the repetitions. Okay? The real number of arrangements will be the combination of 5 taken 2 at a time. And this is equal to n factorial divided by k factorial, n minus k factorial. And this is equal to 5 factorial divided by 2 factorial, and 5 minus 2 is 3 factorial. Okay? This is our conclusion. Only for the women. And how about the men? The men will be the same. There are 3 positions available for the men. Then it is going to be 5, 2. This is the representation of combinations in the binomial form, times 7 and 3, and this is equal to this, 5 factorial divided by 2 factorial, 3 factorial, times 7 factorial divided by 3 factorial, 4 factorial, and this is equal to 350 possible committees with 5 women and 7 men. Okay, my friends, this is letter A. Let's go to letter B now. Letter B now. As there are 2 men refusing to work together, we shall create groups with each of them separately. Let's suppose from the 7 men available, D and F are refusing to cooperate. So this is letter B. We are going to suppose that D and F are refusing to cooperate. That is, they do not want to work together. Okay? For D, we don't. For D, we don't F. We have the combination, okay, of 6 men, okay, occupying 3 positions. 3 positions, okay? Then it is going to be the factorial 3 times the factorial of 3, and this is equal to 20. Likewise, for F, we don't. D, you're going to have the same. We have 6 men available because we excluded D. In this case, we're going to have 6 men available, and they will occupy 3 positions, but we have to discount for the repetition. That's why we are using this 3 factorial here, as we understood in letter A. and this is also 20. Okay? But observe that although for D we don't F, D can participate in the three positions available, it is not mandatory that D is going to be null. We are selecting 6 from the group of 7 men. We have excluded F for D without F, and we have excluded D for F without D. Okay? What does it mean in the end? In the end, that we have 3 positions for 6 men when we exclude F. D can participate, but there will be groups where D and F do not participate. Excluding D now and working with the group of 6 where F can participate without D, there will be groups where F participates but others where both F and D do not participate. Okay? And we are counting these groups without D and F twice here. One for this and one for this. Now we have to remove the groups not containing both D and F counted twice. And to do this, we do the factorial of 5 because we have 7 men minus D and F, it is 5. And discounting the repetitions, we have here 10. Okay? In the end, the number of committees when 2 men are refusing to work together is 5. 2, okay, times 20 plus 20, 20 plus 20 minus 10, and this is equal to 300 possible committees. Okay, my friends, and this is all for this video covering combinatorics. I hope you enjoyed the video and learned from it. I am a teacher, guys. If you want to book a lesson with me, use my WhatsApp number. Goodbye!